Thank you, everybody. It's really great to be here. And do I just use this end of this thing here? Just to the left. Right, okay. So the talk today is entitled Digital Engineering, Data Analytics and Model Calibration, the Future of Building Operation. Very much so focused on a paper that we submitted to the event. So if you're aware of IES and what we provide, it'll be pretty focused in terms of the talk today and what we're looking at. My own name is Nixon, as Emma has said, and I do work as a business development manager for IES. I don't want to labour IES too much, but it does set the context of the talk in terms of who we are. So we're a technology provider. We provide software predominantly and services that go alongside that software. In terms of the types of software, we really focus on building performance analysis. So when you're talking about your heating, your cooling, water consumption, that type of thing, you're dealing with our types of software. And also when it comes to compliance around energy consumption, people tend to use our software for that as well. We're located around the world and used by many of the design team members. They're architects, engineers, facilities managers, and that's only becoming more and more the case with the different types of technologies that we bring and as the market is evolving. In terms of solutions, IES stands for Integrated Environmental Solutions. And 25 years ago when it began, the title of the company still stands today, 25 years on. The idea is that we've got integrated solutions. And so the virtual environment, which many people are familiar with, and some of you may be familiar with here today, as you go and look at your buildings and try and see and predict what the performance of that building will be like at the design stage of the building life cycle, we'll be using the virtual environment. But in the last 10 years, we've been very heavily involved in research and development in the area of building and operation, so that we can come to a point where we're not just sitting isolated with the building at the design stage, but also utilising that prediction technology that we have so that it can be utilised at the operational stage of the building life cycle as well. So a trend that we see, and I'm sure many of you see and have seen, is when speaking to building owners and occupiers, we regularly encounter a situation where the buildings they have had designed and now occupy do not perform as they expect in terms of energy consumption. So a lot of what my talk about today is around that, the energy performance gap, the building performance gap, and perhaps the solution towards solving some of that. When we think about the situation that is encountered, where people are moving into buildings, occupying them, and a year or two on, finding that building is not performing as they had hoped it would, or at least how it had been documented it would, we first of all have to start with their expectations and where they've been set. And in many cases, their expectations are based on things as simple as the building energy rating, the EPCs in the UK as well. And I'll discuss a little bit why that isn't a good approach and what might be a better approach. I'll also look at utilising a combination of building simulation tools and operational building data so that the building owner and project team can make better informed decisions. So you've got this idea of all this data that's becoming available now out in industry combined with the theoretical model and the power that comes with that. And I'll discuss that a little bit. So in terms of our company, one of the little statements that we've used over the years is if you can't measure it, you can't improve it. And that was said by Lord Kelvin. And the company is a Glasgow-based Scottish company headquartered there, even though it is international. So Lord Kelvin is going to come into it. He was speaking more about business when he used this phrase. But I think it very much so applies here, where you've got this idea of needing to measure it, especially when we're trying to push the boundaries of design and really craft it that little bit more. We need to know the numbers and we need to be confident in them. Digital engineering, data analytics, energy performance simulation and calibration now give the opportunity for building owners to measure building performance across the entire life cycle of a building. So even though I'm quite focused here today, we're branching out from design to operation, linking the two of these in terms of our types of analysis. And then we're also doing that with some of our extension of our technology, looking at master planning all the way through to virtual networks and smart cities type approach. Now, part of the problem is also part of the solution here, and that's that in the last few years, obviously the last 5 years in my mind, as I've gone out and as my colleagues have gone speaking to different clients, you've got this idea that data is now becoming more and more available through the Internet of Things, as we've already talked about. So as you've got your building now and they're being built and you're getting your nice BMS systems in there that are capturing the data, even 5 years ago, you went out, that data was not being harnessed, it was not being stored, and it wasn't being reported on very effectively. And even in those 5 years, it's been amazing to see the progress that is being made in that area, and how now there is meaningful information coming out of buildings as they're operating. In terms of let me take a step back actually, in terms of the data, it is still though a slight barrier here, because you have to overcome and make sure you're actually getting into that data and making it meaningful. It's still an issue. It's still an issue out there. We've got data coming from different meter points, different formats and so on, needing to have that in a way that can easily be interrogated and looked at holistically. In terms of another of the issues or problems that we face in this area is the performance gap, which I talked about. And this idea that your performance of your building is somehow listed on as part of your compliance or your BER, Building Energy Performance Certificate. When in fact that has never been the design of that particular certificate. It's just looking at regulated energy. So it's looking at things like heating, hot water, cooling, ventilation, and lighting. So you're very restricted, we're not restricted, but it's very focused on those particular areas for many different reasons. The other things about compliance is that it's based on an activity database, the National Calculation Methodology. And so whenever you think of something like a supermarket or something like this, every supermarket that's being compared for BER is all standardized in terms of these activity types. So it won't represent your building as it's designed. It's important that there's an apples for apples type approach. So you're never going to have your building performance represented in something like a BER. In terms of the unregulated loads, such as your plug loads or your server rooms, this type of thing, these aren't captured in that compliance model. So you need to take it a step further and start incorporating those into your design stage model. So when you think about the model I'm talking about an analysis model. The model where it's a 3D model, you can go in and you can analyze it in terms of these specific types of areas, looking at your heating, your cooling, your electricity loads, and so on. There are other aspects that we need to take into account as well. And those aspects, as you can see, are the extra occupancy and equipment. There's also the inefficiencies from poor control, bad commissioning, bad maintenance, and then special functions as well, where, as it happens, there's extra functions that are needed within this particular building that wouldn't be taken into account within something like a compliance model or some generic type approach. And the opportunity is, there's an opportunity here, and the key finding from a recent design for performance feasibility study was that the power of advanced modelling, now routine in Australia, is rarely used in the UK or Ireland because clients do not ask for it and don't know why they should. So there's some standards out there now, and you think about this kind of approach of building models that are more accurately representing at design stage, that are more accurately representing the building at the operational stage. It is being done, and there's standards out there that can really give you guidance in that. CitA, the Chartered Institute of Building Services Engineers, has brought out a good technical memorandum, TM54, in this area, and they've made great strides. They brought it out in 2013, and definitely people are starting to engage with that. But there's a lot of work to be done within that area. And the idea of that is that you're building up your design stage model, and you're doing it incrementally, so that as the building is moving through the phases, it's the analysis model is being updated all the time. And by the end of that design phase, you've got a really well put together design model, and with inputs, as we talked, someone mentioned earlier on about, I think it was Emma actually mentioned about what you put in, will the end result will be very much impacted by what you put in to the model. So this kind of approach is where you're actually going in and really trying to hone in on good assumptions within your model and accurately modeling in terms of energy consumption and so on. There is the additional cost of undertaking advanced modelling, but it's minimal compared to the return that you can get. And when we think about that return, in 2016, HOK in the US published a return on investment figures related to energy modelling undertaken on their projects. HOK are a large firm over there. They track both modelling costs and predicted energy savings for a large number of projects over several years. They found that the energy modelling was found to have a typical payback period of 1 or 2 months. The most common example of this was through the elimination of oversized and unnecessary expensive HVAC systems. So we're talking about life costs of the building rather than the capital costs. So as you're running that building, the costs that are being saved by going in and putting in the right systems. In terms of the types of buildings they looked at a whole range of different buildings there, and they looked at the percentage of the modelling fee versus the gross capital cost there, and so it's a very small fraction of that. But in terms of the annual modelled energy cost savings, so all the cost savings that are happening annually as a result of that, you can see there that there's some really significant cost savings. And so that's why it leads us to say 1 to 2 months payback period. In terms of the owner, what was said here by Annika Landreneau, owners and project managers do not accept reduced HVAC systems based on energy engineering judgment. They demand to see numbers. Modelling may not be necessary to designing an energy efficient building, but it is necessary to getting that energy efficiency design built. So the idea being that as an engineer, we base a lot of things on experience, and sometimes we can put our thumb in the air and we know the building is going to be within a certain margin. When we want to hone that and we want to really make that building perform excellently well, it's tricky to get anyone to buy into reducing their plant, let's say, and cutting out some of those safety margins, unless you've got some accurate modelling or numbers behind you. So that's where the value in advanced modelling comes in. In the UK and Ireland, the value of advanced modelling is being increasingly recognised as firms such as Arup, Worley and WSP set up building performance and digital engineering groups. Modelling, commissioning and metering. So we've talked about the design stage model. We've talked about going in and creating this more advanced model using things such as CIBSE TM54. Now we think about modelling, commissioning and metering. So a well-developed model which produces an accurate estimation of building consumption is a valuable tool during the commissioning process. As you can imagine, when those are coming in to commission the building are looking at how it's performing, if you've got a good prediction of how that building should perform, then it should aid you in your commissioning process to make sure and identify maybe some faults that might be occurring within your building that you might not see otherwise. Differences between building performance and modelled behaviour can be investigated to determine whether the differences are driven by building faults or by incorrect assumptions in the model. A well thought out sub-metered strategy which provides granular data on end use facilities, this comparison between model and reality, reducing uncertainty in the diagnosis of building issues. So in terms of the data that we're getting out of the model, when you've got this idea of sub-metering and being able to go in and really see how that building is performing, it's very important. It doesn't absolutely have to be there, it just gives us a whole other level when you're comparing these types of models. So a potential solution, this idea of a calibrated model, it's something we've been working on for some time, and there's a number of case studies there that we've worked through with different types of customers. The idea of a calibrated model is the process of improving and verifying the accuracy of a simulated model by systematically comparing that model outputs to real measured data from a building. So as I'm talking about, you've got that real measured data. It really depends what kind of data you've got based on the type of metering you have, but you've got that data, you can compare that to your model and go through that model and get your design model, move it on to being an operational calibrated model. so that it now represents far more accurately the building as it's operating. Now that can be flaws and all, so you're trying to figure out where are these discrepancies in this theoretical model as well. And there are standards coming through there as to how to go and create these calibrated models. Generally, at a minimum, whole building electricity and heating fuel energy will be the key model outputs, but additional comparisons against sub-metering energy improves model accuracy and reduces uncertainty. The applications of calibration are growing rapidly, but can be classified into two main areas: measurement and verification of achieved savings due to the implementation of energy conservation measures, whether that is a retrofit or an operational control measure. So you go in, you calibrate your building, you create really what's called a hybrid calibrated model. The idea being you've got good design assumptions in there combined with the data that you can get from your actual real building and operation. So you have this theoretical model there that accurately represents your building. From there, you can go and you can try these energy conservation measures in the building, try it out theoretically, see which one is the best payback period in your environment and your context. Apply them, invest, go remodel the building with those investments in place, with your energy conservation measures, and see how they're performing. Are they performing as they were designed to? And so it becomes a bit of a circle. Prediction or targeting of future saving, so to assess impact of potential ECMs, as I've just said, before their installation. Undertake fault detection, or use existing past data to set future targets of energy reduction. So that fault detection element in there as well. Such models can be used in identifying suboptimal performance, system faults, and can better determine the measure and verify the implications of proposed energy conservation measures and retrofit options to the building in terms of consumption, cost, and comfort. Another benefit of calibrated modelling is monitoring and targeting. So by using calibrated models, results to define targets for reducing energy consumption is possible to eliminate operational drift within a building. So that whole idea of closing the operational gap between the building in operation and the designed building. The main barriers to calibration can be grouped into issues like the lack of standards, the time and cost and expense of the model development, alongside the need to use different tools, methods to achieve high levels of accuracy. In terms of the calibrated model in action, I'm just coming towards the end of my talk now. The Building and Construction Authority campus in Singapore, we looked at a project there on their campus and looked at the effectiveness of different levels of energy models for different performance analysis requirements, from master planning to calibration at the BCA Academy campus in Singapore. So we looked at a building that was a zero energy building as it stood, and we went and we created this highly calibrated detailed model. From there we got within plus or minus 5% of the performance between the theoretical model and the actual model. So we looked and saw the options to improve the building's performance were virtually assessed ahead of making actual changes in the building. So we went in and made sure they were absolutely very, very close before we went and put in these new types of technologies and aspects. And even in this tightly controlled and monitored building, it was possible, using the calibrated model, to find a number of potential data issues, suboptimal performance, and potential retrofit measures. Their effects and resulting savings were simulated in the model. This included lighting savings of 12% if nighttime lighting was eliminated. And so this particular client can then go see that this 12% in savings is actually met in reality, and if it's not, can look back at the model and say, okay, where are we falling short? What's different? In terms of conclusions, given the benefits presented through the paper, and the paper is quite a bit more detailed than the talk, and is made up of a number of studies that the IES company have done. In terms of that, given the benefits presented through that paper on the use of digital technology and data in the better design and operation of the building stock, the construction industry needs to radically transform its current process to really take advantage of the opportunities in terms of the value associated with those advanced initially design models, and then moving it into combining it with your data from the actual model. Thank you for that. Time is short, so if you have any questions other than now, that's my email address if you're interested in talking further about details. Thank you.